Damping force, or friction, virtually exists in every mechanical system. Here, we put a damper in parallel with the spring. This video will discuss how to solve the equation of motion for this system. Beside of the spring force F sub S, there is a viscous friction F sub D. This will cause the oscillation to decay over time. There will be three cases. Blue line is the overdamping case, green line the critical damping, and red line the underdamping. First, from Newton's second law, we obtain the equation of motion. Next, we calculate the roots of the differential equation. For each scenario, we calculate the numerical solution. The last will be plotting the solution. From Newton's second law, we obtain the equation of motion. The first term is the mass times acceleration, the second is the damping coefficient times velocity, and the third is the spring constant times position. We modify the first equation so that the second derivative term stands alone. To solve it, let's use this trial function. This is the first derivative and second derivative of the trial function. We substitute them into the equation of motion to obtain a more complete expression. We can factor the trial function out. Because the trial function cannot be zero, the term inside the parentheses must be zero. This way, the characteristic equation can be obtained. The quadratic formula yields two possible values of S. Because there are two values of S, the general solution consists of superposition from two independent solutions. For simplicity, let us define the critical damping coefficient, C sub C, and the damping factor zeta. In addition, we also have the natural frequency, omega sub n, which is equal to square root of k divided by m. Conveniently, the expression of C over 2m can be simplified in terms of zeta, and the same can be done onto S. Therefore, we have got the final expression for S. Let us take a closer look at the expression of S. Inside the square root, as you can see, 1 is subtract from zeta squared. If zeta is greater than 1, the result of the square root is positive, so S has a real value, thus causing overdamping. If zeta is equal to 1, the square root is 0. S is still real valued, but this means critical damping. If zeta is less than 1, an imaginary number comes out of the square root, and this is underdamping. To better illustrate the three possible damping scenario, several numerical values will be used. First, zeta equals 2 for overdamping, then zeta equals 1 for critical damping, and last, zeta equals 0.2 for underdamping. The initial conditions for t equals 0 are position equals 1 and velocity equals 0. For the sake of simplicity, the natural frequency is taken to be 1 radian per second. First, let's discuss the overdamping scenario. The general solution x of t consists of two terms. Their difference lies in the exponential and the constants. The constants, namely a and b, are calculated from initial conditions. Their numerical values enable us to write down the solution x of t in more detail. The second scenario is critical damping. The decay term is solely determined by the exponential. The term inside the parentheses arises from two equal roots of the characteristic equation. As in the overdamping scenario, the constants a and b come from initial conditions, and after calculating them numerically, we are able to write down x of t numerically. The third scenario is the underdamping. Here we have the decay term, which is the exponential, and the oscillatory term, which is the sinusoid. The constants that we need to calculate here is k and phi, which can be obtained from the available initial conditions. After obtaining phi and k, we can finally determine the numerical solution of x. Here is the plot for the three scenarios. Blue curve is the overdamping scenario, green the critical damping, and red the underdamping. First, take a look at the blue and green curve. As you can see, in critical damping, the mass reaches zero faster than in overdamping. The underdamping is quite different. There is a decaying oscillation which crosses the abscissa. The envelope of the decay emerges from the exponential term, while the oscillation from the sinusoidal term. Thank you for watching this video. Kindly please give us some feedback by commenting below, and it is very kind of you to support us by clicking like and subscribe. See you in the next video.